Okay, you have a question?
So to prove K cube as a bipartite, do we need to show mathematically or just putting the vertices in two different sets and drawing the adjacency can prove the K cube as a bipartite?
Well, the edges are where the definition is given. You are talking about the K cube.
Yeah, to yes, to show how a K cube graph is a bipartite.
It is the mathematical, a mathematical way is to say in which set to, which vertices to put in set X and which vertices to put in set Y. The edges are already defined for that graph. You cannot decide where to put the edges. The edges, each edge is between two vertices which differ by just one coordinate. That's done, okay? And now you have to decide which vertices to put in X, which vertices to put in Y. And the solution was that one of putting in one of the two, say x, all the vertices whose number of ones is even, and in the other, say y, all vertices whose number of ones is odd. And that's final. And it is absolutely general and mathematical because you have completely described how to build the bipartition. And it's easy to prove that actually it is a bipartition. Why? Because since an edge joins two vertices, if they differ only by coordinate, what does that mean? That for one, that coordinate is 0, for the other, that coordinate is 1, and all other coordinates are equal for the two vertices. And so necessarily, if one of the two has an even number of ones, the other necessarily has an odd number of ones. And so each edge necessarily connects a vertex of x to a vertex of y. And that's it. And it is absolutely general, even if your k cube is with k equal 1000. Okay?
Okay, yeah, it's much clearer now. Thank you.
You're welcome. So let's go now to. I would prefer to start with both of these exercises need, as far I can imagine, need proof by induction. So I want to talk about proof by induction. And I want to set it in a very general way. It is an extremely nice way of proving things, a strange one, but if you have a little experience of writing code or programming a computer, you will see that it's not that strange. So, proof by induction. Oh no! First, I want to say what it is about. It is a proof technique for statements about something which has a size k where k is a natural number. Okay? Example. Call pk the number of permutations of k objects. Theorem. Pk equals k factorial. Okay? And I'll prove very rapidly this example. But how is this technique composed? Two parts. One, inductive premise. Prove the statement for a low k, generally k equal to 1. And this is generally very easy, but absolutely necessary. Two, inductive step. Assume the inductive. Be careful, you have your microphone on. Assume the inductive hypothesis the statement holds. You have a microphone on. Please turn it off. The statement holds for size h minus 1 and prove the inductive thesis. The statement holds for size h. Okay, this looks a bit creepy. Why? How can you assume as hypothesis what you have to prove? But actually, this is very much like a recursive construction. If you have ever done a recursive construction, what do? You make what is called initialization, don't you? And so you have to build something which depends on a certain index I, okay? And what do? What you must do is the initialization. You build the first step, okay? You build that object for I equal to 0 or to 1, but a low, easy thing. Now, then you have a loop of construction in which you assume that you have constructed whatever you want up to I minus 1, and out of it you constructed the next one. Okay? And it is no scandal that you use something that you think that you have constructed something up to step I minus 1. Why? Because you did it for the initialization at step 1. And then you can build step 2 because step 1 has been done. And then you can use the same loop for thinking, okay, the step done has been done, so out of it I can do step 3 and so on and so forth. The same thing is here, not for a construction, but for a proof. If I prove it for k equal to 1, then I can assume that I've done it for k equal to 1, okay? And so h is 2, and I have it for h minus 1. And out of it, I can prove it for h, which is equal to 2. Next, I use h, which is 3, and I have proved it for 3 minus 1, which is 2. And so I can prove it for 3, and so on and so forth. Okay? It sounds strange, but it's very, very powerful. Let's do it for our example. Okay? Uh, I
Excuse
use
me. Please show the previous page once more. The first page of proof in Python.
this. Okay, so we want to prove something. Okay, in our case,
Uh,
uh,
I'm good.
okay, this is the typical example. I want to know how many permutations I have if I have k objects, in how many different ways I can put them in a row, in a queue, okay, and my theorem, my statement is this number p of k is k factorial. Okay. But in our case, in our true case, it's not that. It's, for instance, let's take this. If g is simple and delta is greater than or equal to k, then g has at least one path of at least length k. Okay? This is our statement with something which is of size k. What is this size k? It is this lower bound for small delta. But let me do the simple proof for pk. And so I want to give an inductive premise and then an inductive step. Okay? So let's prove the inductive premise in our example. Sorry. Okay. I use induction for our example. Inductive premise. How much is P1? That is how many, how many permutations are there of one element. As I told you, generally the inductive premise is very easy. If I have just one element, I can put it in a row in just one way. P1 equal to 1, which is actually equal to 1 factorial. Okay, so the inductive premise is done. Now, inductive step. Inductive hypothesis. pH minus 1 equals h minus 1 factorial. Inductive thesis, pH equals h factorial. Okay, I'll do it in the next page. Assume that we have our H objects which are the first H natural numbers. One, two, up to H. Okay? Take H away for the moment. List all pH minus 1 permutations of one, two, H minus 1. Okay? And think we have listed them. I'll do it in the next page. One is surely 1, 2, 3, H minus 2, H minus 1. Okay? But then we'll have something like 2, 1, 3, H minus 2, H minus 1. And then we'll have something very mixed, which might be 3, 7, 2, H minus 1, 4, something like this. In general, we'll have A1, A2, H minus 1, H minus 2, H minus 1, which will be this H minus 1 number permuted in all possible ways, okay? And how many are there of these? The number of these we have said we call pH, sorry, I don't want to, I want it to be very clear. This is pH minus 1. They are in a certain number, which I call pH minus 1. Okay? No, not pK. Oof. pH minus 1. Sorry, I want it to be clear even when you read it tomorrow. H minus 1. Okay? All right, now I think that for each of these I add the number H. Okay, so out of this I get many. In which way? I get H, 1, 2, H minus 2, H minus 1, and then 1, H, 2, H minus 2, H minus 1. 1, 2, 3, um, H minus 2, H minus 1. Here, 1, 2, 3, H minus 2, H minus 1, H. Okay? How many positions do I have for putting my H in all these possible ways? Here at the very beginning, here between the first and the second, and so on and so forth, here as the last by one, and here as the last one. How many are there of these?
H.
Exactly, because of course here, these are H minus 1. Think of them as trees. I have H minus 1 trees. Okay, how many spaces do I have between one tree and another? H minus 2, but I can put my thing, my H, before the first, H minus 1, and after the last, H in node. So these are H. But I can do the same thing here. And so I can do H, 2, 1, and so on, 2, H, 1, and so on, and so on and so forth, up to 2, 1, H minus 1, and 2, 1, H minus 1, H, and these will be H as well. And also here, let me use this last color. What can I do? Of course, I can put H here and then A1, A2, and so on. And A1, H, A2, and so on. And at the end, A1, A2, whatever they are, sorry, I want here an H and then AH minus 1, and finally A1, A2, AH minus 1, H. So, how many do I have? H again. So what can I say of pH? Something is sure. pH, the number of permutations of H objects, is H times the number of permutations of H minus 1 objects. Now, I use the inductive hypothesis. pH minus 1 equals H minus 1 factorial. Then we have, I repeat, pH equals H times pH minus 1. This means H times H minus 1 factorial. But this is exactly H factorial. And the proof. Okay? This is the typical proof by induction. So let's now see sorry, the time. Okay, we have time to face at least this 163. G is simple, small delta greater than or equal to k, then G has a path of length k. Okay? But I prefer a certain formulation which I gave, which is this.
Professor, please show the slides once more from the beginning of the induction proof for a couple of seconds only. I'm sorry.
Sure, no problem, no problem. We have time. Let me see. Okay, this is what you mean?
The previous one, and I get it, and I got it. I took a screenshot.
Sorry?
I'm good. I took a screenshot. Thank you so much.
Okay. Anyway, everything will be put in the web page of the program within 24 hours. Okay? So these two parts, I've used it for this particular thing. Inductive premise, inductive step, I assume this and I prove this. How to prove this out of this? Just by thinking that we list all permutations of the first h minus 1 numbers. I have listed them here. And for each of these, I have h new permutations by adding the number h which was left out before. And so for each we have h. So, of course, we have that the number of permutations of h elements is h times the number of permutations of h minus 1 elements. But now we use the inductive hypothesis, which was that ph minus 1, the number of permutations of h minus 1 objects was h minus 1 factorial, and so we get it. Okay? Now, let's see. I wanted to tell you that I prefer... yes, this. Okay. So I'm going to prove this, which looks stronger, but instead it's not stronger. It is the same thing as what was written in the book. Let G be a graph with the small delta greater than or equal to k, then each vertex of G is the origin of at least one path of at least length k. Okay? I use induction for proving this. So, inductive premise. If small delta is greater than or equal to 0, no, let's do it for 1. For 1, then each vertex is the origin of at least one path of length at least 1. Proof of the inductive premise. That's easy because take any V in the set of vertices. Okay? Degree of V is greater than or equal to 1 because small delta is greater than or equal to 1. So there is at least one edge having ends V prime, where V prime could be a different vertex or the vertex itself. It doesn't matter, okay? Then one edge E, sorry, V prime is a path of length 1 starting in V. As I said, generally the inductive premise is very easy. Okay? So no problem for the inductive premise. Let's go to the hard thing. So, inductive step. Inductive hypothesis. If small delta is greater than or equal to h minus 1, then each vertex is the origin of at least one path of length at least h minus 1. Inductive thesis: if delta is greater than or equal to h, then each vertex is the origin of at least one path of length at least h. Oh, here, what can we say about this h? This h is now greater than or equal to 2, because for 1 we have already done it, okay? For h equal to 1, we've done it in the inductive premise. Okay. So this h minus 1 is greater than or equal to 1. Okay. Let's prove it. G, a graph with small delta greater than or equal to h, which is greater than or equal to 2. Let V be any vertex of G. Degree of V is greater than or equal to small delta, which is greater than or equal to h, which is greater than or equal to 2. Okay? Then Now I would need, sorry, let me see whether the original thing was for, yes, a simple graph, so no loops, okay? A simple graph. So we have no loops. So then there is a vertex, at least a vertex V prime different from V adjacent to V, that is joined to it by an edge. Let now G prime be G minus V. Do you remember what this means? It means that we take away V and all the edges having V as an end. Okay? Let now G prime equal G minus V. What can we say about G prime? Necessarily, we can say two things. One, V prime belongs to G prime, okay? We take away the edge, but we don't take away the vertices adjacent to V. We just take away the edges, but we leave the other ends. And the second thing, what can we say about small delta of G prime? Can we say that it's greater than or equal to H? No. Why? Because by taking away V and all the edges we have in an end in V, we might have also decreased the degrees of some of the other vertices. So what we can say is that at each vertex we have at most taken away one edge. So small delta of G prime is greater than or equal to H minus 1. Okay? But then the inductive hypothesis applies. So at V prime, no, not at V prime, sorry. So, so V prime is the origin of at least sorry, let me give a name adjacent to V, joined to it by an edge which we call E. Okay? Sorry. Then the inductive hypothesis applies. So V prime is the origin of at least one path in G prime of length at least H minus 1. Let's give some names to vertices and edges of this. Okay? This path will be something which is V prime equals, let's call it V1. Okay? And then E1 V2, E2, and so on, up to EH minus 1, VH. Okay, but then going back to G, we have a path. What? This V, E, V1, which is equal to V prime, E1, V2, EH minus 1, VH, which starts in V and has length at least h. Why h? Because here we had a path of length h minus 1, but we had in the very beginning v, e, and so one more edge, which surely is not there, one more vertex which surely is not there because all these vertices belong to G prime, which is G minus B, and so we have a path, and its length is by 1 more than this, and this was of length h minus 1, so at V, at least this path of length h starts. And so we have proved our claim. Okay?
Professor,
Okay?
can you do an example of these notions that we can understand?
Sure. That's a good idea. But please remember.
Because there is too much new notions in 2 or 3 hypotheses, so we can see it in example, so it can be better, I think.
Of course, but please remember, you must learn and be able to repeat the general procedure and also to give an example, okay?
Okay.
Okay. What does all this mean? Let's take a graph. I'll draw a graph like this, okay? Okay, so what? No, 2 is too little. Let's do like this. Okay, so I have that 3 is my lower bound. Yeah, is it? Yeah. Okay. In this case, small delta. This is G. Small delta is actually, in this case, equal to 3, okay? All right, let's take any V. For instance, this one as any other, okay? Let's take this one, okay? Now, of course, degree of V is greater than or equal to 3. Actually, in this case, it is equal to 3. Okay? Now what do? I take G prime, which is this. Are you with me? Let's see what I said. Are you with me with the inductive premise?
Yes.
So let's just focus on the inductive hypothesis, okay? The inductive hypothesis assumes that the thing works for if we have h minus 1 small delta greater than or equal to h minus 1. Okay. But we want to prove it for h. Okay, so I take a graph with delta greater than or equal to h. In our case, h is equal to 3. Okay, we take any vertex, and this vertex has degree which is greater than or equal to delta, small delta, which in our case is 3. And we have actually 3. Then what do we do? Then there is at least one vertex adjacent to it. Which do we want to take? Let's take this. I like this. Okay, so I take this v prime. Sorry. There is at least this v prime adjacent to that vertex. Are you with me? I am following this. Okay. Joined by an edge E. Let's go and call this edge E. Are you all with me, or have I already lost somebody?
No, okay, we are with you.
All right. So now, pardon me?
It is clear. Thank
We are
you.
here.
Yes, but let me end the argument anyway. Now we have G prime, and look at G prime. So this was delta of the whole G. But now delta of G prime is actually smaller because we have that here we have degree 2, okay? And what does my inductive hypothesis say? It says that there is at least one path of length 2. Look, this is a path of length 2. So this is V1, V prime, which I intend as V1. This is E1, this is V2, this is E2, and this is V3. Okay? Actually, I have even longer paths. Okay? But I'm satisfied with this one. Why? Because now I add this. Okay? So I had the path V1, E1, V2, E2, V3 with V1, which was my V prime, and now I can add V, sorry, no, not with this, but with this color, V, E. And so this was of length 2, and now we have this, which is of length.
Professor, I have a question.
Tell me.
The length, number 2.
Length is the number of edges in
Yes,
the path.
length 2, we chose it arbitrarily, right?
No, it is there because it is surely there because we are applying the inductive hypothesis. This is the problem with an example. With an example, you see everything, but in the proof, you don't see anything. You must you must adapt your reasoning to what you can know, and what you can know is the inductive hypothesis. Here you don't see anything, but the inductive hypothesis says, okay, in V prime, there surely starts a path of length 2. Then I add VE and I get a path of length 3, okay? This is the problem with examples. Examples can be very useful, but can be very misleading. What I know is all here. I have the inductive step. All what I know is that if I have small delta greater than or equal to h minus 1, then each vertex is the origin of at least one path of length at least h minus 1. So now I have a graph with a small delta greater than or equal to h. Take any vertex. Okay. Take it away. Take it away. You're left with another graph in which what do you have? You have that small delta is exactly in the situation of the inductive hypothesis. Okay, you cannot say it is greater than or equal to h. In fact, this was well done, even if it was just by luck, that when I take away v, actually small delta decreases. It could not decrease, but I'm pretty sure that it does not decrease more than by 1. So if it was small delta equal to 3 here, it must be small delta maybe 3, but surely greater than or equal to 2 here. And actually, in this case, it is 2. Now, here I see, forget about it. What I know is that in G prime, which has a degree greater than or equal to h minus 1, I have what is said in the inductive hypothesis. So in V prime, as in any other vertex of G prime, you have the origin of at least one path in G prime of length at least h minus 1. Okay, this was our inductive hypothesis. This is all what you know in general. You must be able to reason in general. I am happy to give you an example, but you cannot base your argument on the example. You must base it on reasoning. This is mathematical methods. Okay. And now I'm 1 minute over, and next time we'll do the much more difficult, but more important exercise, this one.
Okay, Professor.
Yeah?
I will try to understand it more by myself. If I find anything or difficulties or something, I will contact you.
Yes, this is a very important part because in the course we'll have many proofs by inductions. Please have a moment for thinking about it. Use the example, but pretending that you don't see that path of length 2. Please pretend that you do not see that, but that you know that you must have it because of the inductive hypothesis. You are not, you feel not safe with this idea of the inductive hypothesis. Go back to the simple example of the permutations, okay? You still have problems, we can discuss the problems separately, by email, by a Teams contact out of the lecture, or even if many of you have such problems, we can go over all this thing again at the beginning of the next lecture next Monday. But think that we'll have also an inductive proof for this, but this is much more difficult than the one we have just seen. So first of all, let's settle very well this example by induction, and then we can try to face this by induction. Okay? Trust me, I do not leave you alone. Okay? But you must act as you are doing. Try to understand. You don't understand? Good, because this means you are working. Okay, so I think it's all for today. See you next Monday. Oh, another question? Yeah. Without your face mask, please.
On the exercise 1.44, on the one for the K cubes, isn't the problem of finding a bipartite graph the fact that every time we can use like K, we can up the K, we can use a greater k, and every bipartite graph in the end is becomes equal to the subgraph of a k cube. I think the only possibility is that we have like two vertices with two edges.
No. A simple bipartite. It is a simple.
A two cube as vertices with degree 2.
Yes, sorry. Here they should have said a simple bipartite graph, because of course, if you put multiple edges, there is no k cube which can have it.
If we take a two cube, we have vertices that have degree 2. If we take 3 cube, we have vertices that.
And so? You must show me.
We can continue and take.
Show me your graph.
But
show me your graph. If I think you attended the Liceo Scientifico.
Yes.
Okay. I want you to become an engineer. So if they say find a bipartite graph, you must take the blackboard and draw. First thing, you draw your graph. Second thing, you prove that no k cube can contain it. But first of all, draw it, then we can discuss. Here, this is a very concrete start. Draw the graph. Second part, it's much more difficult. Prove that no k cube can contain it.
Probably right now I don't.
Okay, but is the problem clearer now?
Yeah, the problem is clear, but isn't the fact that we can, like...
I do not start. I do not accept arguing with you if you do not draw a graph.
I understand.
So you might think this is impossible. Okay. Yes. Okay. This is a nice thing. You might think, but here they do not say. Is it possible or impossible? They state, and I can give you an example. Okay. Find a bipartite. It means a simple bipartite graph that is not isomorphic to a subgraph of any k cube exists. Find one and prove it. So
at the beginning, I thought that there is like I think figure 1.4c on the text. On the bipartite graphs. No, it's the one with 6 vertices. I thought that maybe that one could be, but if we take k equal to 4, I think this bipartite graph is not correct. If we take
it must not be
because we can take a part of a subgraph of the 4 cube, and this graph obviously is then isomorphic to the subgraph.
Okay, so this is not an answer to the problem.
So okay, so we'll think about it. But,
okay, think about it. This is the important thing. Yes. Then when somebody or I will give you the answer, you'll be very happy.
Yes.
Okay.
I hope I find it.
Man, don't be frustrated. Don't be frustrated. As I told you, mathematics is trying, wrong, and maybe always wrong. If you're lucky once, you say, oh, it works. Okay? But don't be frustrated by that. Don't think about it more than 10 minutes.
Okay.
Promise.
Okay.
All right. Ciao to everybody.
Thank you, Professor. Good night.
Good night.
Have a good night. Bye, guys.